Alrighty, we're going to be talking about kind of curve sketching today, as well as a little bit on concavity and kind of what second derivatives mean in terms of our function. So kind of looking back at things we've talked about, if our first derivative is positive, right, that means we have like a positive slope, let's say, so our function is increasing. And then if it's negative, we have a negative slope, so our function is decreasing. But when we have a function, or our first derivative, that is equal to 0, our function is not increasing or decreasing. And we've kind of talked about like where we can have, let's say, some sort of curve. These points here, the function has kind of stopped moving in one direction and it's like a turning point. It's now going in the other. And these are called our critical points, okay? Because this has a derivative of 0 or undefined in some cases, right? So when our first derivative is either 0 or undefined, we have a critical point. Now, this critical point can mean one of two things. These listed here, these are turning points, right? As we're changing from decreasing to increasing, and we can see they are local maximums and local minimum points. But we can also have another point called a point of inflection, and that is where we kind of have something that's going kind of concave down, and then stops, and then starts going concave up. Okay, so we'll talk about how we can identify those two things in this lesson. Let's kind of jump right into it here. So these points here, and I don't really want you to focus on these two functions. Like we're not going to really talk about cusp points or corner points very much, but here is what I want to focus on, right? On this graph, we can see that we have a local maximum value as this point here is the highest point in the curve. And that's this point C, the first derivative of that function would be equal to 0 because the tangent would be horizontal. Okay. Now we could also have the same thing at a local minimum, right? Which we can see here. The tangent is still 0, and it is basically the lowest point of our function in that area. So we call it a local minimum. Now the reason why we use local is because we can have a function that kind of goes up, down, up and down, up and down, right? So in that kind of zone, we refer to just that one point, right? It might not be the overall maximum or the overall minimum, but in that kind of quadrant, that section of the function, it is the highest or lowest points. Okay. Again, our first derivative would be 0 at that point. If you can see that the function is decreasing, hits our point, and then we'll start to increase. Again, not going to really focus too much on the cusp points. The only thing I'm really going to say is that here we can see our first derivative is 0. At these, our first derivative, right, is like an error, undefined. Okay, so it's not something that we're going to focus on a ton, but maybe we'll kind of talk about it maybe a little bit later in the course. Now, here's where I really want to kind of focus in on something that's a little bit different. What happens if you get a first derivative point that is not a maximum or a minimum? So let's take a look at this picture here. Right? At this point, right, we have our first derivative of our function is equal to 0. So we have our tangent line. But that point there is not the maximum, it's right in the middle here. But how I want you to kind of look at this is we're going to use the terminology concave up, concave down. So if I kind of continued with the normal path, this graph should be going up in this direction, right? It should kind of loop up here. But instead, it hits this point and it goes the opposite direction and starts going down, or concave down. And when something switches from concave up to concave down, we call that like a point of inflection, which we've seen if we're graphing, let's say, cubic graphs. Those have points of inflection at x equals 0, right? And here, it's the same thing on the right side, right? We have something that is going concave down, and instead it hits this point and changes to going concave up. The only difference on this one is that our first derivative, right, would be infinite, right? Because it is a vertical, so you're going to get an error, but it's still the same idea. Right. So let's talk about kind of really just the top three here. All right, we can either have a local maximum, which is here, a local minimum, which is here, or we can have an inflection point. And our job is kind of figuring out when we're taking derivatives and we're doing curve sketching, which one is which, right? Because sometimes all three of these values have a first derivative equal to 0, but only two of these are local maxima or minimums, and one of them would be an inflection point. Okay. So let's kind of find the critical points for this function. Now again, critical points, when I use this word, this is asking just to find all functions where the first derivative is equal to 0. All right, so let's jump in here. If I find the first derivative of this function, we're going to get 6x squared plus 6x. All right. Now when I solve this, when is this equal to 0? We have a quadratic here, something that we've done a ton of. And if I factor out 6x, I'm left with x plus 1. And therefore, that's when x equals 0. That's when x equals -1. But remember, this is asking for the critical points, not just the x values. If we're having y values as well, right? When x is 0, if I plug a 0 into my function, well, this would be 0, and this would be 0. So, all right, therefore, the critical points are x equals 0, y equals 0. And at -1, if I plug that into this function, if I do a little aside, right, f of -1 would be 2 times -1 cubed plus 3 times -1 squared. Well, that would just be -2 plus 3, which would be +1. Right? And there we go. We have our two critical points. Perfect. Now, when we're doing our, let's say, our first derivative test, right? We want to make sure something is actually a turning point. We want to see what's happening on either side of our critical point, right? So once we found a critical point, we want to figure out what type of point is it. Now here we can see on either side, if it is a turning point or a local maximum, our function should be increasing till we hit that 0, and then it should start decreasing, right, as we're going down. So we're going up or positive, hit it, and now we're going negative, right? Obviously, if we have the opposite, if we have a local minimum, our function, our first derivative should be negative, it should be going down, we hit that point, and then it is increasing. We have a positive slope on the other side. Right, so when we're doing that test, we can always make sure negative, 0, positive, we're going local minimum, and then when it's positive, 0, negative, it's a local maximum. All right. But here's the different one. If it doesn't change sign at that point, then it is not a local extremum. It's neither a max or a min. You can see here, our function is kind of decreasing. It's here, and then it's still decreasing. So it's going to be negative, 0, negative. Right? Or on the other side, it's going to be going up, 0, so positive, 0, positive. So therefore, it's going to be something else. It's not a turning point, and that's where that kind of point of inflection is going to come into play here. So let's do a hard question. Right? We got ax to the 4 plus bx squared plus cx plus d. We have a local maximum at 0, -6, a local minimum at 1, -8, and we have to figure out what a, b, c, and d are all equal to. Now, right off the bat, what I'm noticing is that because I have a 0, 6 point, if I plug in 0 for x, well, that's 0, and that's 0. So right off the bat, the first thing we can say is, well, d would have to equal -6. Right? Because that's all that would be left in the function. If I plugged in 0, this would be out, this would be out, this would be out, and this value here is -6. That's equal to d. All right, so now I'm going to rewrite my function. I'm going to say if f of x then is equal to ax to the 4 plus bx squared plus cx minus 6, then let's find the first derivative, because when we're talking about local maximums and local minimums, I need to figure out kind of like what the derivative function is, because obviously these are referring to when the derivative is equal to 0. So at this point, we bring down the 4 ax cubed plus 2bx plus c. Perfect. Now, at these values of x, our derivative function should be equal to 0, right? I can't plug the 0, -6 point in because that's the point of the actual function. The only thing that I can plug into my derivative function is that, well, the local max has a point of, well, should be equal to 0 when x is equal to 0. Right? At this value of x, our derivative has a local maximum, which means the first derivative has to be equal to 0. So I'm not plugging in -6, I'm plugging in 0. And now, well, those cancel out, and I'm just left with, oh, c equals 0. Okay, that's another big piece. We have d and we have c so far. So 2 out of the 4 letters. What happens about 1, -8 if I plug that point into my derivative function? Right, what if I go 0 equals 4a, now plug in 1, then 2b times 1. And now c is just 0, so I can just write plus 0. Well, that's going to be 0 equals 4a plus 2b equals 0. Okay, that's one equation. Now, obviously, we're kind of see where we're going here. I need to have one other equation to solve for a and b because I have 2 unknowns. Then I'm going, well, what else can I use to try to get that? But now that I know what c is and I know what d is, I can use my original function, right? So that's equation 1. But equation 2, I can say, well, if I plug in this point into my actual function, right? I can say that -8 is equal to a times x, which would be at 1 to the 4, plus b times x to the 2, plus c, which is 0, x, and then d is -6. Now, when I simplify that, we'll have -8 equals a plus b minus 6. And if I move that -6 to the other side, I have -2 equals a plus b. And look at that, just like that, I now have 2 equations that I can solve for. 0 equals 4a plus 2b, and then -2 equals a plus b. And now, right, we'll do substitution or elimination with this equation, doesn't matter which one we do. And I'm going to write equation 3. I'm going to rearrange equation 2, and I'm going to write that as a equals -b minus 2. I'll sub equation 3 into equation 1. So then I have 0 is equal to 4 times a, which is -b minus 2, plus 2b. 0 equals -4b minus 8 plus 2b. Then 8 would have to equal -2b, or -4 would have to equal b. All right, so there's 1 point. And now all I have left is a. So then I'll sub b equals -4 into equation 3. And then I have a is equal to, well, -b, which is -4 minus 2. A equals 4 minus 2. And therefore a equals 2. Right? So therefore, f of x, let me zoom in here. If a is 2, our first function, let me kind of move this over so I have space. Therefore, f of x is equal to ax to the 4 plus, well, this will be minus because b is negative, minus 4x squared. C is equal to 0, so I need to write that term. And lastly, d is -6. All right. And there's some stuff working with first derivatives.